Usually when you think about taking a test, you picture like sitting at a desk, right? You've got your number two pencil, a completely quiet room, maybe you're bubbling in a Scantron sheet or just typing on a laptop. It's a very static, controlled environment. The absolute biggest danger in that room is, maybe giving yourself a paper cut.
Right, exactly. Or, maybe drinking way too much coffee beforehand and getting the jitters. But the environment itself is just entirely passive.
But then you look at something like the TESDA Machining NC Disaffected assessment in the Philippines. Suddenly, the test is literally a live, spinning piece of heavy metal. You're stepping into this industrial environment where, honestly, a single unbuttoned sleeve, a stray measurement of a fraction of a millimeter, or just reaching out your hand at the wrong second can end your exam instantly. It's this high-stakes crucible of precision, extreme safety, and just incredible grace under pressure. Welcome to the deep dive. Today, our mission is decoding exactly what it takes to survive and pass this rigorous trade assessment.
And, because we're dealing with some incredibly dense, high-stakes technical material today, we're talking about the physics of metalwork, strict occupational safety laws, the exact mechanics of industrial machines. We are going to take this at a very deliberate, steady pace. We aren't going to rush through this.
Right, no rushing at all.
Exactly. Whether you're listening to prepare for a trade exam yourself, or you're just deeply curious about the sheer, meticulous skill required to shape solid steel, we want to make sure every single concept lands clearly. It's all about that careful, reasonable pace, just matching the exact kind of craftsmanship this assessment demands.
Okay, let's unpack this. Because where does the pressure test actually begin? It seems like, reading through this, it starts long before you ever touch a piece of metal.
Oh, it absolutely does.
Right.
The assessment has officially begun the very second you step foot inside that room.
Hmm.
And the foundational layer of this entire process isn't your ability to cut metal. It's your ability to exist in a machine shop without creating a hazard. Yeah, under the Philippine Occupational Safety and Health Law, so that's Republic Act 10058 safety, is entirely non-negotiable.
Right. It reminds me of like a high-end, high-stakes cooking competition. Think about it. If you show up to a Michelin star kitchen and your station is just a greasy mess, or you aren't wearing your chef's coat properly, the head chef disqualifies you before you even chop a single onion. It feels exactly like that, but, with lathes and milling machines.
That is a really brilliant way to look at it. Safety is the ultimate benchmark here, and the assessors are looking for automatic red flags right out of the gate. For instance, if you operate a machine without the assessor's explicit go-ahead, you're done.
Just like that.
Just like that.
Yeah.
If you remove a machine guard because you think, oh, it'll help you see the cut better, you are done. And personal protective equipment, or PPE, is an absolute baseline. You need safety glasses, ear protection, and if you have long hair, it absolutely must be tied back and secured.
I actually want to pause on that for a second, because for someone who doesn't work in a shop, tying your hair back just sounds like a dress code thing, like a uniform standard.
Yeah.
But in a machine shop, a spinning spindle doesn't care if it catches your sleeve or your hair.
Not at all.
It will literally pull you into the machine with thousands of pounds of force. So it's not a dress code, it's survival.
Exactly. And that is why a safety violation results in an automatic, not yet competent grade. It was basically the assessor's way of saying you failed.
Right.
There's no level of machining skill, no matter how flawlessly you shape that metal, that can offset a safety violation.
Right.
And it even extends to how you maintain your space. Housekeeping has to be a continuous, active process. You don't just sweep up at the end of the day.
Okay, so you're wearing the right gear, your area is clean, you are totally respecting the machinery, you're safe. But a safe machinist who doesn't know what they're actually building isn't much help either.
Right, exactly.
That leads us right into the blueprints, interpreting the engineering drawings. And reading through this material, it seems like misinterpreting a drawing is the fastest way to just doom a project before it starts.
Yeah, and what's fascinating here is how assessors actually test your comprehension of those blueprints. Because they don't just ask you if you understand it, they expect you to restate the drawing back to them out loud before you ever make a single cut.
Oh, interesting. So instead of just nodding and saying, yeah, got it, you have to actually narrate the dimensions. Okay, this blueprint shows a 32 millimeter shaft, and I need to turn it down to 28 millimeters over a length of exactly 80 millimeters.
Precisely.
Yeah.
And there's a very deep cognitive reason for this, Engineering drawings are incredibly complex. You're taking this flattened, two-dimensional piece of paper and trying to visualize a three-dimensional object in your head.
Right. It's like mental gymnastics.
It really is. By verbalizing the dimensions and the sequence of operations, you prove to the assessor that you genuinely comprehend the job. But more importantly, it forces your own brain to double-check that spatial data. Assessors use this drawing phase to sort of open their oral questioning, because if you don't truly understand the blueprint, you have absolutely no business touching the machine.
Well, and a perfectly drawn blueprint is entirely useless if the metal spins so fast that it just melts the cutting tool. That's why the absolute next hurdle isn't physical, it's mathematical. We have to translate those drawn lines into numbers the machine can actually use.
Right.
Now, I do have to push back a little here. We are talking about massive, expensive, highly advanced industrial machines. Why on earth do I need to stand there doing math in my head or scratching it out on paper without a calculator? Can't I just, load the steel into the machine and guess the speed based on how the cut looks or sounds?
Oh, guessing is incredibly dangerous. It is dangerous to you, it is dangerous to the tool, and it will absolutely destroy the workpiece. This whole assessment is designed to prove that you operate on exact knowledge, not on luck.
So no winging it.
Definitely no winging it. You have to prove you understand the physics of what is happening when a sharp tool meets spinning metal. And that brings us to the most critical piece of math in the entire exam, which is the spindle speed formula.
Okay, let's walk through that formula, but let's do it slowly. Because imagine you're standing in front of an assessor, the machine is off, the room is quiet, and you have to calculate surface speed in your head. That sounds honestly terrifying.
It is terrifying, which is why we really need to understand the physics of it first. Imagine a classic vinyl record spinning on a record player.
Yeah.
If a bug lands right in the center near the label, it's just slowly rotating in a tight little circle.
Sure.
But if a bug lands on the absolute outside edge of that record, it's flying around at a much faster speed to cover that wider distance in the exact same amount of time.
Right. The outside edge just covers way more ground.
Exactly. Now replace that record with a thick cylinder of solid steel in a lathe. The outside edge of that steel is flying past your cutting tool. If the piece of metal is very wide, the outside edge is moving incredibly fast.
Okay, I'm tracking.
If you don't slow the machine's RPM down, the revolutions per minute, that sheer speed will basically burn up your cutting tool in seconds. So you have to adjust the machine's RPM so that the speed of the metal hitting the tool remains constant, regardless of how wide the cylinder is. That constant speed is called your cutting speed.
That makes total sense. So the formula is just the mathematical way of solving for that RPM. It's N, which stands for RPM, right? Equals 1,000 times the cutting speed divided by pi times the diameter of the metal.
Perfect, yes. And let's break down where those numbers actually come from. The cutting speed, which is your target surface speed, varies entirely depending on what you're cutting.
Yeah.
Like mild steel requires a totally different speed than soft aluminum or hard brass. You pull that target cutting speed from a standard chart.
Let's do a real example just to ground it. Say I'm working with a 32 millimeter mild steel shaft, and I'm using a standard high-speed steel cutting tool. A machinist knows that material dictates the speed. So let's say the chart says, I need a cutting speed of about 30 meters per minute.
Okay, so you plug that in, you take your cutting speed of 30 and you multiply it by 1,000. And you might wonder, why 1,000? It's simply to convert meters into millimeters so all your units of measurement match up perfectly.
Yeah.
That gives you 30,000.
Okay.
Now you divide that by pi, so roughly 3.14 multiplied by your diameter, which is 32.
Right, so 3.14 times 32 is roughly about 100. And 30,000 divided by 100 is 300. So I need to set my machine to 300 RPM. I really love that.
When you understand the why, that you're just trying to keep the surface speed steady so the tool doesn't literally burn, the formula isn't just random letters anymore. It tells a story.
It really does. And the assessors will catch you instantly if you just memorize the letters without understanding that story. The most fatal trap here, honestly, is unit conversion.
Oh, like imperial versus metric. Yes, exactly. If an assessor gives you a diameter in inches, say 1 inch, and you forget to convert that to 25.4 millimeters before plugging it into the formula, your calculated speed will be wildly, dangerously off.
Wow. Okay. So we figured out how fast the machine needs to spin. But the math doesn't stop at speed. We have to talk about tolerances, because this is where the pressure really spikes. In machining, a tolerance is basically the allowable variation above and below your target dimension. So let's say the blueprint calls for a shaft to be exactly 20.00 millimeters plus or minus 0.05 millimeters.
Right, so that means the absolute largest the part can be is 20.05 millimeters, and the smallest it could be is 19.95 millimeters. Anything inside that tiny window is a pass.
Wait. So if I'm allowed plus or minus 0.05 and I measure my part and it is 20.06 millimeters, that means I am 1/100th of a millimeter off. To put that in perspective for you listening, a single human hair is about 0.07 millimeters thick. Do they really fail you for being off by a measurement thinner than a human hair?
Yes, they absolutely do. It's a straight reject if it, feels close or if it looks perfect to the naked eye. It literally does not matter. An engine block or an aerospace component doesn't care if it feels close. If it's 0.01 millimeters too large, the bearing just won't fit and the engine fails. So a correctly machined part that is out of tolerance is an automatic defect on the score sheet.
That is intense. And obviously, you can't measure a fraction of a human hair with a standard ruler. You have to choose the exact right instrument for the job, and the assessor is watching to see if you know which one to grab. Like, a basic steel rule is fine for rough, general checks, but when you get into these tight tolerances, you're basically choosing between a vernier caliper and a micrometer.
Right. And you really need to understand the mechanical limits of each one. A vernier caliper is incredibly versatile. It's got jaws for measuring the outside of a part, smaller jaws for the inside of a hole, and a depth rod. It relies on these sliding scales aligning with each other, and it's highly accurate, usually down to about 0.02 millimeters.
Which sounds tiny.
It is. But if your tolerance is tighter than that, say you need an accuracy of 0.01 millimeters, the caliper just isn't good enough. You absolutely must reach for the micrometer.
The micrometer is the one that looks kind of like a C-clamp, right? With the little thimble you spin to close the gap.
Exactly, yeah. It uses a highly calibrated internal screw thread to carefully close the anvil and the spindle around the part. It is purely for high-precision, outside diameters.
There's actually a fantastic pro tip for this phase that I found really fascinating. Seasoned machinists strongly advise speaking your instrument readings out loud as you take them, like 28.12 millimeters. Why is narrating your measurements so helpful?
Well, it serves two really massive purposes, actually. First, it completely short-circuits transcription errors. The journey from your eyes reading those tiny lines to your brain processing the number to your hand writing it down on paper, it's just full of trapdoors.
So much room for error.
Exactly. By hearing yourself speak the number, you're actively verifying it. And second, it visibly signals ownership and confidence to the assessor. Because assessors will frequently just walk up to you and ask you to read an instrument cold with no part attached, just to check your raw technique. Speaking clearly shows you aren't second-guessing yourself.
Okay, so the safety foundation is laid, the math is dialed in, and you know how to measure the results. Now finally, it is time to actually cut metal. But as you move from station to station, the bench, the lathe, the mill, it becomes clear that every single machine has its own completely hidden trapdoor for failure. Let's start before we even power up the big machines. Let's talk about bench work. This is the phase that relies entirely on human hands, right? Filing, sawing, drilling, and tapping threads.
Yeah, and tapping is notoriously the highest failure operation at the bench. For those who don't know, tapping is the process of manually cutting internal threads into a hole so a bolt can screw into it later.
I try to picture tapping like buttoning a dress shirt. If you start with the wrong buttonhole at the very top, it doesn't matter how perfectly you button the rest of the shirt. The entire thing is misaligned all the way down, and the only way to fix it is to completely undo it and start over.
That is a perfect analogy, except, well, with metal, you can't just unbutton it.
Right.
If you start a tap at an angle, you're cutting crooked threads into solid steel. It cannot be corrected afterward. The piece is just scrapped. You must square the tap, meaning you use a small square to ensure the cutting tool is perfectly 90 degrees vertical to the metal. But the absolute critical secret here is that you have to check it from two different positions, 90 degrees apart from each other, before you make that first full cutting turn.
Because if you only check it from the front, it might look perfectly straight, but it could be leaning heavily to the left or right, and you wouldn't even see it until it's too late.
Exactly.
Yeah.
It requires a complete three-dimensional awareness of the tool.
Here's where it gets really interesting. Once you survive the bench, you move to the lathe. And the lathe is all about how setup errors propagate. If you set your tool height slightly wrong, or if you leave too much of the tool hanging out of the holder, that physical error bleeds into every single cut you make for the rest of the exam.
Which is exactly why the assessors are watching the first 2 minutes of your setup incredibly closely. They're literally judging you before a single metal chip flies.
And there is a golden rule on the lathe that stands out above everything else. Always take a light first trial cut. I was thinking about why this is so heavily emphasized, and it really comes down to the permanence of machining, right? If you need a shaft to be 20 millimeters and you take a massive cut and measure it and it's 21 millimeters, well, it's oversized. You can just adjust the machine and take off 1 more millimeter. But if you cut it down to 19 millimeters,
It is completely ruined. You cannot put metal back on. Recovering from an undersized cut is literally impossible. So taking a light, really shallow trial cut, then stopping the spindle fully and taking a precise measurement, that is the ultimate safety net for your tolerance. It tells you exactly how the machine is behaving before you commit to the final depth.
It's so permanent, and the operations themselves are so distinct. You have facing, which cuts across the end of the cylinder to make it perfectly flat and perpendicular. You have turning, which travels along the length to reduce the outside diameter, and boring, which goes inside to enlarge a pre-drilled hole.
Right. And then you transition to the milling machine, which presents an entirely different set of physical dangers.
Yeah.
A lathe spins the metal against a stationary tool, but a mill holds the metal completely stationary in a heavy vise and spins a multi-toothed cutting tool against it.
And the physics of how that spinning tool interacts with the metal is a huge oral questioning topic, specifically the difference between climb milling and conventional milling. Actually, I want to spend a second here because the mechanics are wild.
Oh, this is a vital concept. In conventional milling, you feed the metal against the rotation of the cutter. Imagine the spinning teeth of the cutter scooping up from the bottom of the metal and pushing away. It naturally pushes the workpiece safely back into the vise. It's the safer default on manual machines.
But climb milling is the exact opposite. You feed the metal with the rotation. So the teeth of the spinning cutter are coming down onto the top of the metal and essentially trying to drive over it like a tire on a road.
Yes, and that creates a massive physical hazard on older or manual machines. If a machine has any slack or looseness in its gears, what machinists call backlash climb milling will violently grab the workpiece and pull it forward into the cutter.
Just yank it right in.
Exactly. It can literally rip the metal out of the vise, shatter the cutting tool into shrapnel, and cause severe injury. Now, climb milling leaves a beautifully smooth surface finish, but you only do it on rigid, modern machines designed to handle those extreme forces.
That is terrifying. If you engage the machine in the wrong direction and initiate a climb mill when you shouldn't, it isn't just a minor deduction on your score. Assessors treat that as an immediate safety stop. The exam is just over.
It loops right back to that RA 11058 safety standard. The moment you create a hazard that threatens life or limb, your skill simply no longer matters.
Okay, so you know the math, you know the physics of the machines, you know the safety rules, you've planned everything perfectly. But what happens when the perfect plan goes wrong? Because, let's be real, it always does. This brings us to the final hurdle, the oral scenarios. These aren't just technical questions, they feel like actual psychological tests of character.
They absolutely are. Assessors refer to this as a test of contingency management. They really need to know how you react when the unexpected inevitably happens on a loud, busy shop floor.
Let's run a scenario. Let's say I am on the final finish pass on the lathe. I've spent 3 hours on this part. I stop the spindle, I take my micrometer, and I carefully measure my part. It is 0.03 millimeters outside the allowable tolerance, so it's undersized. There is no metal left to remove to fix it. Do I try to hide it? Do I just confidently hand it to the assessor and hope they don't check that specific spot?
This raises an important question about integrity in the trade. The only acceptable answer here is radical honesty. You stop, you go to the assessor, and you tell them exactly what happened and exactly what you measured. You do not try to pass it off.
Wait, really? Even though I know admitting it means I've produced an out-of-spec part?
Yes, because honesty about a measured defect scores far better than an attempt to conceal it. Remember, they aren't just grading your hands, they're grading your eyes. If you pretend a bad part is good, the assessor assumes you either lied or your inspection skills are so poor you genuinely couldn't even read your own micrometer. Covering it up means you fail the machining aspect and the inspection aspect.
That makes total sense. Integrity is really part of the safety culture. What about a physical crisis? Say you're mid-cut and the lathe suddenly starts to chatter loudly, just a horrific, vibrating, screaming sound.
The human instinct, especially under the ticking clock of an exam, is to just grit your teeth, push through, and finish the cut. But pushing through chatter is the absolute worst thing you can do. The vibration will actually shatter the tungsten carbide insert of your tool and leave a destroyed, wavy finish on the metal. You must immediately back the tool out and stop the feed.
And then what?
Then you methodically diagnose. Is the tool hanging out too far? Is the workpiece loose in the chuck? Is your speed too high? You solve the physics problem before you ever resume cutting.
What if the crisis isn't even happening on my machine? There's a scenario that asks, you notice a co-candidate at the mill next to you has removed a safety guard because they're struggling to see their layout lines. Do I just mind my own business and focus on my own exam?
Absolutely not. You flag the assessor immediately. A removed guard means flying hot metal chips or a shattered tool could launch across the room. Their hazard is your hazard. Staying silent reflects incredibly poorly on your own workplace safety awareness.
Here is a really stressful one. You look up at the clock, you're running out of the allotted time, and you still have one entire operation left to do. Do you crank up your feed rates and speed up to finish the part before the buzzer?
No. You maintain a normal, safe working pace. You communicate your status to the assessor, just acknowledging the time. A slower, incomplete, but highly accurate and safely machined part scores immensely better than a completed part where you rushed, compromised the tolerances, and bypassed safety checks. Rushing in a machine shop always leads to catastrophic accidents.
They really want to see you diagnose problems dynamically, too. An assessor might walk up and hand you a deliberately flawed sample piece like a piece of metal you didn't even machine, and simply ask, what is wrong with this?
It's a brilliant diagnostic test. It completely isolates your inspection knowledge from your physical machining skill. If they hand you a part and the dimension is way oversized, you need to be able to tell them that the previous machinist likely took an insufficient final cut or just failed to set their tool offset properly.
And if the part has a taper error, meaning it's a perfectly round but wider at one end than the other, you deduce that the tailstock of the lathe was misaligned, pushing the metal slightly diagonal to the cutting tool.
Exactly. And if they hand you a part that is covered in sharp, jagged burrs on the edges, you diagnose that the machinist skipped the critical deburring step, or maybe they used a severely dull tool that tore the metal instead of cutting it. And you point out that a burr isn't just ugly. It prevents a micrometer from sitting flat, meaning the part can never be accurately measured. Plus, it will literally slice your hand open the moment you grab it.
So, what does this all mean? When we step back and look at this entire deep dive, the non-negotiable safety laws, the record player physics of the spindle speed, the irreversible trapdoors of the lathe, the radical honesty required when you mess up, it reveals that the TESDA machining NC thick feet isn't just about memorizing facts or having steady hands.
Exactly. It highlights the 4 pillars of a true professional in this trade. Task skills.
Yeah.
Can you physically operate the heavy machinery? Task management. Can you read a complex blueprint and sequence the operations logically? Contingency management. Can you handle a chattering machine or a dull tool without panicking? And finally, workplace awareness. Do you protect yourself, your environment, and the people working next to you?
It's a totally holistic view of a machinist. They aren't looking for just a pair of hands to blindly pull levers. They're looking for a disciplined, thinking professional.
If we connect this to the bigger picture, the ultimate lesson of this assessment is about standardizing excellence. You are expected to practice with the exact same rigorous standards as the actual exam, doing it perfectly in practice, measuring twice, narrating your steps out loud to catch errors, and deeply respecting the destructive power of the machine. That is the only thing that actually prepares you for the pressure of the assessment room.
I absolutely love that. It's all about building the right habits before you ever need them under pressure. And it leaves me thinking about a principle we can all take away from this. Even if you never step foot inside an industrial machine shop, think about that golden rule of the lathe, taking a light first trial cut to test your setup. Or the benchwork rule of squaring the tap from 2 different angles to make absolutely sure you aren't starting crooked. How could you apply that kind of deliberate, measured approach to avoid irreversible mistakes in your own life or career? Whether you're starting a new project, signing a contract, or just having a difficult conversation sometimes, we all need to take a light trial cut and check our angles before committing to the full depth. Thank you so much for joining us on this deep dive. You are now a little more well-informed and definitely ready to tackle whatever blueprint comes your way.